Now let's go through some examples of floating point numbers. So let's talk about normalization. We mentioned that there's an implied 1 before the fraction. That's this 1 point f right here. And why is that there? Well, I told you it's because it forces only a single representation of each number. And as we saw from the sign magnitude discussion, having a single representation is generally good. So let's take a look at an example of what happens if we don't have that normalization. So here we're going to look at a number with a 3-bit fraction. So here's the format we have, minus 1 to the s times 0 point f1, f2, f3. Those are our 3 bits of sign value times 2 to the exponent. What we're going to do for this representation is we're going to figure out different ways we can represent the number 2. So here's one representation, 0.100 times 2 to the second. This is 1/2 times 4, which is 2. But we could also shift over by 1. So we could 0.010 times 2 to the third. This is 1/4 times 8, which is also 2. And we could do this again. We could shift over one more bit and have 1/8 times 16, which is also 2. So the problem with not having normalized numbers is there are lots of ways to represent the same value. And this is a waste of our number line. So if we have an implied 1 there, then we only have one way to represent 2, and that's 1.000 times 2 to the first, or 1 times 2. So here's a question. If we have a 23-bit mantissa and no normalization, how many ways are there to represent each number? Or at least each number that's a power of 2 if you want to be specific. So how many ways could I shift the value 2 here and still have 2 if I have a 23-bit mantissa? Well, the answer is 23. If I have 23 bits of my mantissa, I could shift it over 23 places and still get the number 2. So that's a real waste of how we store numbers. That's why we use normalized numbers to force us to only have one representation. So, how are floating point numbers spaced out? Let's take a look at this because they're not the nice linear spacing that we have with regular integer numbers. So we're going to look at an example 7-bit floating point number here. That is 1 bit for the sign, 3 bits for the exponent, and 3 bits for the fraction. And here's how they're spaced out, and this is on a linear scale. So you can see it's clearly non-uniform. If you look down here in the smaller numbers, we have lots and lots of values, but they're spread out much further up when we get larger numbers. So overall, we can cover numbers from very large down to very small, but we do not have a uniform coverage. If we plot this on a log-log graph, we see much more uniform coverage. So in particular for the normalized numbers, on a log-log scale, we have a very nice uniform coverage of the number line. So here's a question. Why are the numbers distributed logarithmically? What is it about the floating point format that makes them look linear on a log-log scale? So if you look at the floating point format, it's because we have this 2 to the exponent in there. Because we're doing 2 to the power of something, when we take the logarithm, we end up with a nice linear distribution. So we should expect that our numbers are going to be somehow spread out logarithmically over the number line because we have an exponent in our number representation. Now you can play tricks with floating point numbers, and this is one of them. These bits down here at the bottom, these numbers, those are non-normalized numbers, or d-norms. You can get these extra numbers if you allow yourself to have non-normalized numbers. And so most floating point implementations allow non-normalized numbers because then they can get a little more resolution. So now we're going to talk a little about doing math with floating point. We're going to talk about floating point addition and floating point multiplication. So here's an example. We want to add 2.1 times 10 to the 12th and 9.2 times 10 to the 10th. So the first step in doing this is to rewrite them so their exponents match by shifting the mantissas. So we don't shift the one on the left because it's got the largest exponent, so we would keep that as 2.1 times 10 to the 12th, but we have to shift the one on the right. So 9.2 times 10 to the 10th is the same thing as 0.092 times 10 to the 12th. I've shifted it over 2 places, and I've added 2 to the exponent. Now I can go ahead and add the mantissas, so I add 2.1 and 0.092, and I get my result. But before I do that, I have to round the result. So when I round off the result, I get 2.2 times 10 to the 12th. So what did we do to do addition? We shifted, or multiplied, the smaller number so that we could match the exponents. We added the mantissas together, and then we rounded to fit into the number of bits we have. So this is much more complicated than integer math. It has additions in it, but it has the shifting, and you have to have far to shift, and you have to round. You may also lose precision here. So if you look at the smaller number we added, we lost almost all of it. We ended up only adding 0.1 to the bigger number, even though we had 9.2 for the sort of precision of the smaller number. I'm going to talk a little bit more about this later. So floating point multiplication, how does that work? It's different from addition. In fact, it's easier. So here we're going to do the same thing. We're going to multiply 2.1 times 10 to the 12th times 9.2 times 10 to the 10th. But now we're going to multiply instead of adding. So we multiply the mantissas. 2.1 times 9.2 gives us 19.32. And we add the exponents. 12 plus 10 is 22. Then we round and shift the decimal places over to make sure it's normalized. And there's our result, 1.9 times 10 to the 23rd. So what did we do for multiplication? Well, we multiplied the mantissas and added the exponents. We shifted to put the decimal place in the right place, and then we rounded. So this is much simpler than floating point addition. We don't have to change the numbers depending on which one has the larger or smaller exponent. But we still need a big multiplier. So for floating point numbers, you need a 23-bit multiplier, because we have to be able to multiply the mantissas. And for double precision numbers, we need a 53-bit multiplier to multiply their mantissas. So now we're going to talk about losing precision. I mentioned earlier that you can lose precision if you have big and small numbers, and let's take a look at that. So say I have a big number plus a small number. Well, we saw that the result is going to be pretty close to the big number. We don't have the precision to keep the small number's information around when we're looking at a big number. Here's an example. I'm going to add 2.1 times 10 to the 20th to 9.2 times 10 to the 5th. So this is a number that's 10 to the 15 times bigger. So to do that, I need to take the smaller number and I need to rewrite it with the exponents matching. So if I rewrite 9.2 times 10 to the 5th so that it matches the exponent, what you can see here is I have to shift it way over. This is 0.00000092 times 10 to the 20th. And when I add these together, this 2.1 is so much larger than this 0.00092 that it basically disappears. And this is from having to shift to match the exponents before adding. Now what happens if I then subtract off big? Do I get small back? So I had big plus small, and now I'm going to subtract big. What do I get? Well, if we had perfect precision, big plus small minus big would be small. But what we saw here is that big plus small is about the same as big. We've lost precision because we have numbers of such different magnitude. So big plus small minus big is about the same as big minus big, which is 0. So I don't get small back. I get something very close to 0. So remember that nonlinear distribution of numbers. When we have a very large number, we don't have the precision to store very small numbers in addition. We get to choose with floating point numbers. Do we want to have very large numbers that we can represent, or do we want to have very high precision but much smaller numbers? And that's what moving the binary point around does. So the real problem here is if you try to divide by the result. So now if I try to divide by the result of 0, I get something divided by 0, and that's infinity. And so that's bad. So what you've learned from this is the order of operations matters. For example, if I did it the other way around, if I do big minus big, then add small, I get small. Because big and big are the same order, so when I do operations with them, I don't lose precision. So this is a real problem, and it means you have to be very careful when you're writing math libraries. The good news is people have done this for you. You shouldn't be writing your own math library. You shouldn't be writing your own linear algebra code. You shouldn't be writing your own FFT code, because getting these things right is really tricky, and there's really good code out there that does it for you. So remember this. If you're dealing with numbers with very different magnitudes, very large numbers and very small numbers, floating point can't keep all the details around, and you're going to lose some information from that. So let's summarize how we deal with non-integer numbers. We had two ways of doing this. We had fixed point numbers and floating point numbers. So fixed point numbers were just like integer math, but we specify where this binary point is going to be. This is great if you know the range of your numbers beforehand, not so good if you don't. Floating point numbers are more flexible. Where that binary point is, how big a fraction it is determined by the exponent. So we have three parts in the floating point. We have the mantissa. That's the fractional part, which has the precision. The exponent, which determines where that point is. Where do we put the binary point? Is this a large number or a very small fraction? And then you have the sign, which is positive or negative. Remember, there's a nonlinear scale here, so you can get much higher precision with small numbers, but you can get a very large range. Addition is also complicated. We mentioned that you have to shift the exponents to match before you can do addition, which makes addition slow. Multiplication is reasonably simple. Division is unbelievably ugly, and you don't want to think about that. Combining small and numbers will lose precision. We saw this example. If you do big minus small plus big versus big minus big plus small, you get different results. And the real truth here is that floating point numbers have lots of nasty issues. All sorts of corner cases and strange things that happen, and we haven't even touched on them in this lecture. I'll be happy to post some more notes on floating point numbers if you want to read more about it, and there's tons of information about this on Wikipedia, but I'm not sure I'd really recommend it because you'll probably get a headache from reading all the details.